So continuing from where we left off with the conditional probability as well as the multiplication law of probability, this session we are looking at the Bayes theorem, which is also affiliated to this conditional probability. Now this Bayes theorem is applicable in situations where quantities of the form A, probability of event A given B, and probability of B are known. However, we wish to find the probability of B given A. So in this case, we could have a situation where this entity, that is probability of A given B, will be known, and this probability is also known. However, we wish to estimate B given A. Okay, you can see that in this case, A happens to be the first and BI happens to be the next, but we like to have the probability the other way around. No, so before we go through with this, there's this general rule that we have to go through, which is termed as the law of total probability, which we will go through very soon. But this Bayes theorem is really a simple application of the multiplication rule and goes back to Reverend Thomas Bayes, who lived in the 18th century. Now, just as I said, before we get to see this Bayes theorem, let's get to understand what this law of total probability really is. Now, recall from our previous session that suppose that you should have event A to K which are mutually exclusive. That is, if these two terms have nothing in common, then the events are exhaustive if one of the event must be so that their unions could be estimated as their sample size. Okay, now suppose that let's event A1 to AK be mutually exclusive and exhaustive events. Then for any of other event B, we have probability of B is equal to probability of B given A1 times the probability of A1. This is going to continue until it gets to the last case. So there's going to be a sequence of these conditional probabilities times that of their single-handedly events. So because this is a summation, all this could be represented as a summation of the probabilities for B given AI times the probability of AI, okay, from A running from I to the last event, that is K. So let's see how this total law of probability works. After that, we transfer that knowledge to the Bayes theorem. Now with this, we are looking at messages and email. And with this, we are looking at an individual who possesses 3 email accounts, which is in my case, I possess about 3 email accounts. So in my case, most of my messages, let's say roughly about 70% come into my first account, that is account number 1, whereas about 20% come into the second account and the remaining 10% goes into my third account. Now, of the messages that come into account 1, only 1% are spam, whereas the corresponding percentages for the account 2 and 3 are 2 and 5% respectively. So what is the probability that a randomly selected message is a spam? And this happens to be our question. So before we get to do that, let's get to denote some notations here. So suppose that AI happens to be, let it represent the message that is from account number I. And remember, we are dealing with 3 accounts, that is account 1, 2, and 3. And let B be an event such that a message coming into a certain account is a spam. So from the question, the various percentages have been given. The probability of event A1 that happens to be message going into my account 1 is 70%, which will have to be 0.7. The probability of messages that is going into account 2 is 0.2. That of the last one being 10%. Now it was also given that the probability of a message being spam or being given that it is account 1 was given to be about 1%, and the probability that the messaging spam given that is in account 2 was equal to what? To 2% and 5% for what? The last what? Account. Now that we have these notations here, for us to get the probability that the random selected message is a spam, all that we have to do is to simply substitute this into what? The total law of probability, that expression, which we had to be the whole thing that we have here. So let's get to see this. So in this, all that we have to do is just multiply the first one, that is the conditional probability, by the probability of A1, as we have here, plus the probability of A2, plus the probability of A2 as we have here. In that same case, we are going to multiply 0.5 as we have here by its probability, and that is going to give us what? 0.16. Okay, so this is telling us that there is a probability that about 1.6% of the individual's mail, or in this case, which is my mail, will be made out of what? Spam. So this is how we get to make use of what? This total law of what? Probability. That is when we get what? Sum the product of the conditional probabilities as well as that of the probabilities of the individual events, sum everything together, and that gives us what? This law of total probability. Now with this knowledge, let's try to transfer this to the Bayes theorem. So with this Bayes theorem, suppose that we have events A running to K, a collection of mutually exclusive and exhaustive events with prior probabilities of A1 up to the number of events that we are looking at. Then for any event B for which probability of B is greater than 0, the posterior probability of B of A I or AJ is given to be, given that B is given by probability of AJ, given that B has is equal to what? The conditional probabilities as we have here. But this is the case that we have several events for this A, okay, and that is what we have in here. So all that we have to do is find the conditional probability, then multiply by that, then finally we are going to find the summation of all the probabilities of this. And remember, this is what we learned from the law of total probabilities. So we are going to just estimate that and just put it here. So let's take an example, see how this works. Okay, so with this, there's an incident of rare disease occurring at a certain vicinity, and out of this, only 1 in 1,000 adults is affected with this rare disease, for which a diagnostic test has been developed. Now the test is such that when an individual actually has the disease, a positive result 99% of the time, whereas an individual without the disease will show a positive result only 2% out of the time, which is to say that the sensitivity of this test is 99% and the specificity is equal to 98%. Okay, now these are terms for checking or evaluating the performance of what? Models. This is something that you guys will be coming across if you should venture into model development, that is modeling. Those of you who will be entering into disease modeling, and that you get to need this sensitivity and specificity also there. So our sensitivity is being given by 99% and our specificity is equal to 98%. Now if a randomly selected individual is tested and the result is positive, what is the probability that the individual has the disease? Okay, so let's see how we get to use the Bayes theorem to arrive at an answer. So in this case, let our A1 be equal to the individual having the disease, and A2 the individual does not have the disease, and an event B a positive test result is being achieved after testing this individual. Then from the question, we could see that the probability of A1 was given to be 0.0001. Now remember that we said that 1 out of 1,000. So 1 out of 1,000 is afflicted with this rare disease. So the probability of getting the disease is 1 out of 1,000, which is equal to 0.001. Now the probability of not having the disease is equal to what? Out of 999 out of 1,000 will not get the disease because it is a rare disease. So that is why we are having a probability of 0.9999. So it's more or less like 999 out of what, 1,000, and that gives us what? That, okay? Now the probability that the test is positive, given that the person really has the disease, we have that to be 99%, and that is why we are having the 0.99. And the probability that the person has the test is positive, given that the person that does not have the disease is equal to 2%, which we have to be 0.012. Now let's see how we get to represent this on the tree diagram. So with this disease, rare disease, is either you have it or you do not have it. Now if you have it, the probability of the test being positive is equal to 99.99, and that is 99% as we have in here. Now the probability of you having the disease but the test failing to diagnose you is equal to 0.01 as we have in here. So if we would like to note or determine our probability of A1 intersection B, this is the same as 0.01 times 0.09, and that is going to give us 0.9999. Similarly, if you don't have the disease, the specificity of the test is 0.2, that is that is the 2%, which is the same as 0.02. So if you would like to determine this probability of A to intersection B, that is the probability of not having the disease, but the disease or the test is going to identify you as 1 or going to diagnose you as positive, is will be equal to 0.12998, as simple as we have here. Okay, so if you like to determine the probability that individual has the disease, that will be the probability of this first one that we have here plus the probability of 0.09 we have here, and that is going to give us what? 0.02, as simply as that. So this is just going to help us determine the probability that we shall need in estimating our conditional probability, okay, as we have down here. Okay, so with this, for us to estimate that the probability of achieving or the model or the test diagnosing you to be positive, given that you already have the disease, is equal to a probability of this as we have here to be 0.999, 0.0099 as we estimated right here, all over this probability as we have to be 0.12 as we have right from here. So if we should go through this and simplify, we are getting 0.47. Okay, so remember that probability of A1 intersection B is what we have here, and the probability of B is what we have down here. Okay, we just simplified here, and that is what we have. So this is how we get to make use of the total law of probability and the Bayes theorem to achieve our intersections as we require. Okay, simple as that. So remember from this section that we were given probability of B given our A's, but however we were interested in probability of A given B, and once that situation come by, we use the Bayes theorem to help us achieve this. So with this result of 0.047, this result is some kind of counterintuitive. That is to say that the diagnostic test appears to be so accurate that we would expect someone with a positive result to be highly likely to have the disease, whereas the computed conditional probability is only 0.047. However, the rarity of the disease implies that most of positive test results arise from errors rather than the disease individuals. The probability of having the disease, which has increased by a multiplicative factor of 47, that is from the prior 0.01 to the posterior 0.047, but to get further increase in the posterior, a diagnostic which is much smaller error rates will be needed. So this brings us to the end of how to use this Bayes theory to estimate conditional probabilities as well, and also to the end of problems and so on. Now with all these videos, remember that if you should have any difficulty in understanding any part of it, make sure to let me know. You can text me, you can send me a message through either the Google platform, that is the Google Classroom, or that of the VLE, and I will respond as such. So go through this and take care. So enjoy the rest of the day. So enjoy that.